I'm gonna start recording, and but this part was review of the previous video. So if you look at the previous video, I discussed this part in much more details. Okay.
Okay, perfect. Thank you.
All right. Thanks for reminding. And it is being recorded now. So any questions from this concept of setting depths or the equivalent mod density concept?
So very much basically like you just when you go to the point close to uh, the kicking, you said kicking merge,
Kick merging. Yeah,
and that's what you're gonna go horizontal.
exactly. Yeah. Yeah. Because if you continue, and if you look at your mod density compared to the fracture gradient, let me kind of make it a bit look nicer here. If you continue with the same mod density here, right? Then at some point, your mod density, which is constant, you use the same mod density, will be higher than the equivalent mod density of the fracture gradient, right? So that means that if your mod density is higher than the fracture gradient, that means that you will frac the formation, because the hydrostatic pressure will be higher than the frac resistance of your formation. So you will frac your formation. So you shouldn't continue with the same mod. You will all the way go until you hit the trip merging line. And then you go vertically upward, again, do the same thing. Any other questions? Well, for your project, you will have to develop these lines to find these pore pressure, fracture pressure gradient lines, draw the kick merging and trip merging lines, and set the casing depths, and then design the casing. That's what you have to do for your project. And then you will learn, starting today, that how to draw these curves, how to find these basically pressures. All right. Any questions? No. All right, so let's continue. Now, what is the normal pressure? Normal pressure is when you have, let's just consider that you have a container, right? And you fill it with water, right? And there is nothing, no porous media, nothing, it's just full of water, right? As you go down in this container or pool, whatever you call it, the hydrostatic pressure increases, right? It's exactly like you have your drilling fluid inside the wellbore. Your hydrostatic pressure increases based on the mud density that you have, right? So this is called normal pressure gradient. But when you talk about the normal pressure gradient for underground formation, you are considering the pressure gradient, the hydrostatic pressure gradient of the water that you have there on that area. Okay, some areas the water have some salt in it, some of them are lighter, some of them are heavier. For example, you can see that for West Texas, it's 0.433 psi per feet. Gulf of Mexico 0.465 psi per feet, and different areas you see that they have slightly different, right, normal pore pressure gradients. Okay, and it depends on the water that you have there. Now, when we talk again about a normal pore pressure gradient, that means that your hydrostatic pressure changes linearly with depth. That's the normal pore pressure gradient. Starting from the surface all the way to the bottom, right? And then you see that the reason that you have a constant hydrostatic pressure is that all those formations from here, surface, all the way to that depth that you have the normal pore pressure gradient, somehow the pores are connected together. Okay, so there is a communication between all these formation, and there is water, for example, in all those pores, and all those pores are somehow connected together hydraulically, and that causes that your hydrostatic pressure to become basically linearly changing with depths. Okay, so that's the definition of normal pore pressure gradient. And you can see here also these pores are somehow connected together, all they have water, right? And the overburden stress, which is basically the weight of the rock that you have at any depth. For example, overburden stress is a pressure. I think we didn't define overburden in this class. No. So overburden means that you have whatever weight of the rock that you have above that formation. That means overburden stress. Okay. And that overburden stress or pressure is basically transmitted by forces between different grains. So this grain on the top puts some force on this one. This one adds some force to this one, right? This is how much, and each of them have some weight, right? Or mass. And based on their mass, they exert some force on the bottom grains, right? So this is called overburden stress, which we'll talk about it again in this lecture. And and also in terms of the, again, normal pore pressure, all these fluids are connected together. So hydrostatically connected, and the hydrostatic pressure changes linearly with depths. Okay. Any questions here? Now, you saw in the first figure that we had there, right, that equivalent mud density is constant. So it means that up to this depth, you have a normal pore pressure gradient. It means that all the pores from this depth all the way to here are connected hydraulically. Pressure changes linearly with depth. It means that you have same equivalent mud density all over, right? Now, what happens here is abnormal pressure, which is basically what we want to talk. And there are many reasons for abnormal pressure that we may kind of touch on some of these reasons. So one of these is basically under compacted shale. So look at this picture, see what you see here. Okay. Let's say you have basically this system here, right? A piston, and then you have a bucket which have some fluid in it, right? And let's say this system is underground, right? And there are a lot of water on the top here, right? And this water have some hydrostatic pressure that exerts on this piston, right? Now, this bucket is connected to a line that can transfer the fluid. So if there is a pressure exerted to this water, the water can escape through here, right? Now, let's assume that there is a valve here and this valve is closed. And then you apply a huge overburden pressure from sediments. In this case, let's assume that it's just water on the top, right? To this water which is inside this bucket. Now, the water can't escape, right? What happens is that you have an extra pressure of the water inside that bucket, right? Because the water can't escape to the surface, and there is a huge pressure being exerted to that water, right? That's exactly what happens underground. This huge amount of water that you see in this picture is basically in the actual underground formation. We call it overburden stress. And this overburden stress is coming from the weight of the rock underground. Okay. Now, I don't like this equation here. You see an equation here. It's called overburden stress is equal to pore pressure plus matrix stress. I like to write it another way and saying the matrix stress, which I will define it for you, is equal to overburden stress minus pore pressure. It's the same equation. I just changed the way I write it. Okay. Why? Because overburden pressure or a stress is kind of defined. It has a physical meaning, okay? And the meaning of overburden is, again, the weight of the rock that is being applied to any formation on the top of it, right? So from zero depths all the way to the depths that your formation is, there is a huge amount of rock on the top exert gravitational force, right? On the formation. That is called overburden stress. And pore pressure is also clear concept, right? Because you have some fluid and this fluid is under the pressure, so it applies some force. So if you have a pore, you have fluid in it, and this fluid have some pressure and it exerts force to the wall of that pore, right? So that is called pore pressure. And the difference between these two, which are two opposing forces, is called matrix stress. So this is an effective stress, basically, right? That is due to two opposing forces acting on each other. One is the overburden stress due to the rock, and one is the pore pressure, which is due to the fluid, right? So these two opposing forces act on each other and be defined basically a matrix stress. Now, what happens if you have all these fluids overburden stress here, exerting force on your pore, but then the water cannot escape? There is no communication between your water and the formations on the top. So let's assume that this is your formation. Let's say you have water or some fluid here. This is surface. You have all these rocks on the top of your formation that have a huge weight, which we call it overburden, right? Applies force to your formation, and then the water cannot escape anywhere else. It is stuck here. Okay, so your pore pressure increases, right? Because the water cannot escape to anywhere else, and some pressure is being applied to it, right? So the water pressure increases, right? Now, in normal pore pressure gradient, however, since all these pores are connected together, so if there is a pressure due to overburden, then that water can escape to somewhere else, right? But in abnormal formation pressure, that water cannot escape the formation due to a couple of reasons. One reason is that you have a shale formation on the top of your actual formation. And as you know, shales are very low permeable and very low porous type of rock, right? So they do not allow your water or oil or gas, whatever you have, to escape from it. And that's why we call it trap or formation rock, because it cannot escape really, right? So you will see that your pore pressure will be abnormally pressured because there is no communication between that reservoir rock or any other type of rock with the other formation. So that's one of the main reasons that we have um, abnormal pressure. Okay. Any questions here? All right, so no question. Let's continue. You have shale, you might have fault, that basically anything that disrupt the communication between your formation and other rocks around, that could cause abnormal pressure. Okay, so it could be fault, it could be a shale, anything that basically prevents that, a dense cap rock, right? That anything that basically prevents the communication between your formation and other type of rocks above or bottom, it is basically a cause of abnormal formation pressure, right? Now, anything, what else? For example, you're drilling a wellbore here, right? And you had basically some erosion happened, and you are basically here, right? Your actual land was here if you continue, but your land have eroded for after millions of years, right? And now here is your surface. You drill a wellbore, you go all the way down to the formation that you wanna, let's say, drill through. And that formation is, let's say, an aquifer. Aquifer is a formation that have water in it, 100% almost. We call it aquifer. And that formation is actually continued all the way in this direction, all the way here, and that is connected to the surface somehow, right? So the actual formation pressure that let's say it's not connected. Yeah, it shouldn't be connected. Let's say here is sealed, right? Now, your actual hydrostatic pressure of that water at that depth is actually this one, 0.052 density delta H. And since this formation, all of them are connected together, the formation pressure is this one. But when you drill a wellbore, you think that the normal formation pressure gradient should be 0.052 multiplied by density multiplied by Z, right? Now compare delta H with Z. What happens? Delta H is much higher than Z, right? So this number, the actual formation pressure, is much higher than you expect it to be, right? So that's another cause of abnormal formation pressure. So you think it's abnormal. It's not really abnormal because this formation is connected to some higher altitude formation area, right? And they are all connected. So the actual formation pressure is this one. But since you're drilling at this depth, based on this Z or the depths of the formation, you think it's abnormal, right? And it is abnormal. You might have formations that are going this way, and then suddenly your formation pressure spikes, okay? So that's another reason that you might have abnormal pressure, right? Now, let's say you drilled another road. Another reason is basically a low density pore fluid, right? So you might think that you're drilling here and then you drill the wellbore here, you're going, everything normal, you hit a saltwater formation, everything normal, right? Now, since this saltwater and these gas formations are connected together, uh, here you have a basically gas sand here, right? But it means that you have gas inside this reservoir, right? And gas is very low density fluid, right? So the pressure that this gas sand have is basically the pressure at this depth, let's say, right? It's a high pressure, right? And the thickness of this sand formation is 300 feet, right? And since all these are connected together, this is just one formation, all these gas sands are connected together. So the pressure at this point and this point are equal because gas really doesn't have any hydrostatic. Its density is around 2. So the hydrostatic difference from the top of this gas sand to the bottom of this gas sand is only 31 psi due to the weight of that gas, right? The density of that gas. So once you hit here, you think that you have very low pressure, but actually your pressure is really higher than what it should be, right? Because you can see here, for example, the pressure at water oil contact, water gas contact. This means water gas contact, which is here, is 0.052. Normal pore pressure gradient on that area is 9. The depth is 1300 feet, so the pressure is 608 psi. Now the gas hydrostatic, which is 300 feet column of gas, is only 31 psi. So the pressure at this depth which is 577 psi. Now, let's say this is 300, right? So this is 1,000 feet. So you can calculate the density, equivalent density here, which is 11 pound per gallon. So 577 psi, which is the pressure at the top of this formation divided by 0.052 divided by depth is 1,000 feet. So the actual equivalent density at the top of your gas sand is 11 while you think it is 9, right? So that's an abnormal pressure again, right? Any questions here? Nope. So these are all the reasons. Another reasons are man-made sources. So man-made sources are, for example, you did a very poor job in your cementing, or you did a poor job in the casing, you selected the wrong casing and your casing broke, right? And then you have leak to some permeable formations, right? So leaking to permeable formation basically causes the actual formation pressure that you have there to be less than what it is, right? So there are some man-made errors as well that could cause the misinterpretation of the formation pressure. Now, these are kind of overall reasons. You can look at it when you it's also in the book. You can check that out. But what we want to do here is basically talking about the types of measurements that we can do in terms of the formation pore pressure. Now, some of the measurements are before drilling, some of them are during drilling, some of them after drilling. Okay, and we'll talk about each of them separately. And usually, the way we do it is basically when you do during the drilling. I mean, there are before drilling that usually are through seismic. If I write it correctly, seismic interpretation. So they sound acoustic wave underground. They receive it back at the surface, and then you can find the pressures underground, the formation pressures underground. We're not going to talk about this. This is part of the geophysics that they do. But during the drilling, there are ways to do that. And one of the ways is basically to use the well likes that we do. And porosity is one of the indicators of the formation pressure. Now, if you can somehow establish a curve that how your porosity, so what do you guys think? The porosity, well, it's mentioned here, porosity decreases with depths, right? What is the reason for that? Why do you think porosity decreases with depths?
Overburden pressure increases.
Yeah, exactly. So overburden pressure increases. Rocks are pretty much the same strengths, right? I mean, yeah, of course, there are different types of rocks, but overall, the overburden pressure increases. Let's say if you have a shale, right, and that shale is at the shallow depths, or that shale is at the very bottom, right? So of course, the porosity of this shale at the very bottom is much less than the porosity of this one, because there are much higher overburden stress at these depths, right? So if you can establish a porosity curve along the wellbore, right, it should linearly change if you plot it on a log-like plot. So these are based on the experience that the porosity changes exponentially with depths. It means it drops basically exponentially with depths. And if you plot it on a log scale, then you will see a linear line. And they do it especially for shale. They use shale as a clean shale as one of the rocks that they establish the curve for. And they look at the shale and they check the porosity values at different depths of the shale, and they establish this linear line, which means that your porosity is decreasing. And then at some specific depths, they will see that their porosity suddenly increases. And this is an indication that your formation pore pressure is higher than what it should be, because you have an extra force that causes your porosity to increase, right? And that is the pore pressure, right? Now, comparing the actual porosity with the normal, with the extrapolation of the normal trend, you can basically use some of the correlations that we will discuss later on to find the pore pressure at that depth. Okay, so these are in general one of the methods. Another method is basically to compare the effective stress at different depths. So let's say you have basically established that porosity, right, curve. You extrapolate that normal. This area is called normal compaction, and establishing this line is called normal compaction trend. Okay, so this is normal compaction trend. You extrapolate that line, and your actual porosity is actually like this, right? Now, at this point, if you go vertically until you hit the normal curve, these 2 points have the same effective stresses, right? The difference between overburden and pore pressure, we define that, right? So these 2 points, since they have the same porosity, it means that the overall force being acted, because, and they are the same type of rock, both are shale, right? They will have the same, they have the same porosity, and that means that they have the same effective stress being applied to them, and definition of effective stress is overburden stress minus pore pressure, right? So you can put sigma v at this point equal to sigma v at this point, and that means that you can write overburden stress minus pore pressure at depth d, overburden stress minus pore pressure at depth de, put them equal to each other. Overburden stress is pretty easy to calculate. Usually it's 1 psi per feet, increases with that rate. And then there are ways to calculate that as well, but it's pretty easy to find. And then you have the pressure at the normal gradient, right? So you can calculate the pressure at that formation. So this is another way. So one way is this way that we use correlations, right? Comparing the same depth porosity values, right? One of the main equations that we will discuss is called Eaton's equation. That's a correlation, which uses this method. Another way is use the equivalent depths method, which basically uses the same effective stress depths and then put equal to each other. Okay. Does it make sense? Any questions here? Now, we will do calculations on that, so don't worry about it. Many porosity indicators can be used. Now, we talked in general here about the porosity, but there are many porosity indicators as well. Do you guys remember anything from rock and fluid properties when we used to calculate porosity using some of those logs? Anybody remember those logs? What logs did we discuss in rock and fluid properties? Nope. Nobody remember? Well, one of those logs was density log, right? So if you remember, the equation was density, porosity was equal to density minus density of matrix divided by density of matrix minus density of fluid, right? So we had such an equation to calculate the porosity using the well logs. Well logs were devices that you send into the wellbore. They send some sort of signal into the formation. They receive it back, and based on analysis of that receiving signal, we can determine different properties of the rock. We can determine the saturation using resistivity log. We can calculate the porosity using density, or sonic log, and was another one, right? Sonic log basically was a type of log that it sends acoustic waves into the formation and calculate the speed of those acoustic waves in different formation and convert that speed into porosity. And you can calculate that using, it calculates basically a travel time, which the unit is microsecond per feet. And this is actually 1 over velocity of that acoustic wave. And based on the measured, this is the measured delta T. This is delta T matrix, means that purely the rock. And then delta T matrix minus delta T fluid. I might have written it the other way around because I believe matrix is still here and fluid is here, I guess. Anyway, we discussed this in rock and fluid properties. You will learn more about these logs in your formation evaluation course next fall, but we want to use those type of logs to find the porosity. Now, delta T indicator, this is sonic log. This is density log. Density should increase with depth, but if you see that your density is not really increasing anymore, that's a trend that shows that you have a abnormal formation. The delta T should basically drop as you go down, and delta T should also increase. I think it's no, yeah, delta T is basically dropping, and then you can establish the normal compaction trend. You see the actual values from the well logs, and then you can use any method to calculate the formation pressure at those depths, right? Conductivity, rate of penetration, DC exponent, which I will show you the equation for, It's basically, I will talk about it. These are also the type of measurements that shows the porosity, and of course you can use them to calculate the formation pressure. Any questions so far? Now in your project, I think I gave you the sonic log and conductivity or resistivity. I gave you resistivity. I gave you these two logs to choose from, whichever you want, and establish these normal compaction trend, find the actual value, use any of the methods to calculate the pore pressure gradient at any depths. And you would need that for your casing design, right? Why do we need that? Why do we need, again, the pore pressure?
They said casing.
To set the casing depths. What else? One of the reasons is that one.
Figure out your mud density.
To establish the mud density. What else? Any other reason you guys think when you design your casing? Why would you need the pore pressure? Any varying calculation of casing design? No? Burst, collapse, tension, any of these designs uses the pore pressure? Well, remember, for burst pressure calculations, what you do is you multiply your pore pressure by the design factor, and that is your burst pressure. So you would need your pore pressure when you design for the burst requirement, right? So therefore, this basically pore pressure with depths is important for you because you would need to have that for your burst design criteria. And that's the only place. Yeah, we don't use it for tension. We don't use it for collapse. For collapse, we use the mud density. Make sure you go and read and practice that casing design example that I posted online. That's a 3-weight casing design because that would help you for your casing design project as well. Okay. All right. So I think we are almost done. It's 12:45. We'll go over, we'll continue on Monday on this topic. So probably we will finish this chapter on Monday, and we will start the fracture on Wednesday. Do you guys have any questions before we leave?
Could we have like an example, like with the pore pressure?
Yeah. I haven't started talking about how actually we calculate these. So we will go over the before drilling again. We will talk about during the drilling. We talk about the after drilling. So all the methods I will cover next time, and we will do some examples next time too. Okay. So
Once
yeah.
once you do like a casing design, do you need first you calculate the pore pressures and like on
Yeah, so the steps for that is basically what you need to do is first to find the setting depths, right? Find setting depths. in the very general format, right? Establish your mod program, right? That's the second step. So basically these two is done at the same time, right? Using those pore pressure and fracture pressure gradient curves, right? Then you start to design your casing, right? So design casing for each section of the wellbore that you are designing, from surface, intermediate, production separately. And in the design, you do the burst first, right? Then you do the collapse with all those equations. Then you do the tension, and you are done. Okay, so this is basically general procedure that you would do for designing your casing. In your project, you do all these steps. In the extra point homework, you only do the design part. So any
Thank
other
you.
any other questions? Nope. All right, so that's it for today. I will upload these slides, which mostly was theoretical, right? So I will upload it, but next time we'll actually start doing those calculations for pore pressure, and on Wednesday we'll continue on fracture pressure.